Hello, welcome back. Here we're going to conquer the topic of the geometric series. Now, of course, we've already talked about the geometric series in several lessons, but we never calculated the sum of the terms of the geometric series. So just like in the last lesson, we talked about the arithmetic series. We introduced the concept of the arithmetic series. We talked about the sum. We wrote the equation down, and I proved it to you, and then we solved problems. We're going to do the exact same thing for the geometric series. I'm going to introduce it. I'm going to motivate it. I'm going to write down the equation for the sum of the terms of the geometric series. Then I'm going to prove it to you mathematically, and then we'll solve some problems. So let's take about the simplest geometric series that I can think of to motivate the point here. So this is a geometric series. How about 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. So I just tried to pick something that's easy to understand with finite numbers. How many terms do we have? 1, 2, 3, 4, 5, 6, 7 terms. So there's 7 terms. And how do we know it's geometric? Geometric just means that to get the next term, you take the previous term, you multiply by the same number, by a common ratio. So to go from this term to this term, we actually multiply by 2. To go from this term to this term, we multiply by 2. To go from this term to this term, multiply by 2. This term to this term, multiply by 2. And I could keep writing it. You could see multiply by 2, multiply by 2. So this is a geometric series. And the common ratio, r, is equal to 2. This is the common ratio. All right, so what I want to do is I'm going to write down the sum of these terms. I mean, we've written these things down, we've done the summation convention, but we haven't actually calculated the sum of any of these geometric series like this. So let's go ahead and write that down. The sum of the geometric series is as follows. The nth partial sum, which means we sum the first n terms, is equal to the first term multiplied by 1 minus r to the power of n, all divided by 1 minus r. Okay, that's what I want you to remember. Now, is it obvious that this is the case? No, but we're going to prove it in just a second. Now, the one thing I want you to point out to you here is that the only thing you need to calculate the sum of these terms, I mean, I know you can add them in your calculator, but I'm saying, what if you had 1,000 terms? That would take forever. How do you calculate the sum? Well, you put the number of terms in place. You have to know n. You have to know the common ratio r. That's what you're multiplying by to get these terms. R is down here as well. And you have to know the first term. So you actually don't need to know the last term in order to do this. Remember, for the arithmetic series, we needed the first term, we needed the last term, and we needed the number of terms. Here, we do not need to know the last term. We just need to know what is the common ratio, what is the number of terms, what is the first term. Now, notice in the denominator we have 1 minus r. And because we have that in the denominator, what we really need to say out here is that this equation holds for the sum. However, r cannot be equal to 1. Why? Because if I put a 1 in for the common ratio, 1 minus 1 is 0, and we're dividing by 0, that's really undefined, or you could say that it goes off to infinity. So either way, when you divide by 0, it's not going to work for a calculation. So you cannot have r common ratio equal to 1. But when you think about it, that's not a big deal, because if I had a common ratio of 1, what would the series look like? If I take this and multiply by 1, I'm going to get 1. Multiply by 1 again, I get 1. Multiply by 1 again, I get 1. So if the common ratio were ever 1 for any series, technically it's geometric, but it's a boring series, because every term is just going to be the exact same term. So if I wanted to find the sum of the terms of a geometric series with a common ratio of 1, I don't need this fancy equation. If all of the terms are the same, I just take the first term and multiply by how many terms I have. If the first term is 5, then every term is 5, and I just say 5 times however many terms I have, and then I have the sum. So it's kind of boring, and it's not really helpful, and so it isn't a big deal that r cannot be 1 in this equation. For any other geometric series, this equation is going to work. Now, before we actually prove this, I want to mathematically prove it to you. Before we actually do that, I want to apply this to this known geometric series that we have above. So we just said that the nth partial sum is the first term times 1 minus r to the power of n over 1 minus r. That's what we said. And we said we have 1, 2, 3, 4, 5, 6, 7 terms. So for this particular series, we know that n is equal to 7. We know that the first term is equal to 1. And we know that the common ratio, because we just wrote it down here, the common ratio is 2. So we have everything needed. So let's check it out. the seventh partial sum is the sum of the first 7 terms, is going to be equal to this first term, which is 1, times 1 minus the common ratio of r, 2, to the power of n, however many terms we're adding together. And on the bottom, it's 1 minus r. So 1 minus r is 2. All we have to do is do this calculation. Okay? So the 1 times this, the 1 is going to disappear. So all you're going to have on the top is 1 minus, what is 2 to the 7th power? You're going to have 128. Wrap it in parentheses if you want. On the bottom, 1 minus 2 is going to be negative 1. So what are you going to get? You're going to have S7. You're going to get 1 minus 128 is negative 127 over negative 1. So the 7th partial sum is positive 127. So what we're basically saying is that if we add up all of these terms, we should get 127. And I encourage you to do that. Grab a calculator and say 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. You're going to figure out that that's exactly equal to 127. Now for a series with 7 terms, it's not a big deal to add them up. But what if this geometric series had 1,000 terms? What if it had 1,000,000 terms or 15 million terms? And adding them up, even with a computer, would take forever, right? It would take a long time, even with a computer. So this equation is mathematically calculating what the sum of however many terms of the series I want. All I need to know is the first term, the common ratio, which lets me predict all the future terms, and however many terms I want to consider, it's going to add them up. Now, the question is, why does it work? Right? Now, as I said in the last lesson when we derived the arithmetic series formula, in math, when you prove things, all you care about is arriving at this. You want to prove that this is true, and you can do anything you want legally to get there. So what we're going to do is we're going to write down the terms of the series. We're going to, in this case, this is a geometric series I wrote down with numbers, but we're going to write down a general geometric series. And then I'll walk you through the next steps to get from point A down to proving that this is the equation that describes the sum. Mostly, I don't want you to memorize this, but mostly I just want you to know that these equations don't come out of thin air, right? So how do we do it? Let's take a look at this proof. What I'm going to suggest, or what I'm going to say, is that the nth partial sum is going to be the sum of all the terms of the geometric series. Every series starts with a first term, so we call it T1. What is the next term in the series? Well, for a geometric series, to get the next term, all you do is you start with the first term and you multiply by a common ratio. To get the next term after that, you multiply by the common ratio. It's always the same pattern. So to get the next term, it's just going to be that first term times the common ratio r, T1 times r. But then how do you get the next term after that? It's going to be this term times r, but then times r again, so it's going to end up being T1 times r squared. When you think about it, you multiply by 2 and you multiply by 2 again, so basically you consider it being 1 times 4 to give me 4. So I can predict any future term by doing this. So this is the pattern like this. And then let me ask you another question. Well, let me go ahead and get it down. What would the last term be in the series? In the last term here we had, notice we had 7 terms, 1, 2, 3, 4, 5, 6, 7. There's 7 terms. How many multiplications do I need to get there? 1 multiplication, 2, 3, 4, 5, 6 multiplications. So if I start with the first one and do 6 multiplications, I get to the 7th term. So in the general form, the last term is going to be the first term times r to the power of n minus 1. So we start with the first term to get the next term multiplied by the common ratio. Then we multiply by the common ratio again, and I'm saying we keep doing that until we get to the last term, but the last term is r to the n minus 1. Why is it to the n minus 1 for the last term? Why isn't it just r to the nth? Well, it's because if there are n terms in the series, if there's 7 terms in this series, I do 6 multiplications to get there. So this is the last term, the nth term, so I do 1 less multiplications by r to get there. That's why it's n minus 1. What would the term just before that be? It would be T1, let me erase this plus and make it clear, T1 r to the n minus 2, because, again, we're multiplying here, so this is multiplied by r to the n minus 1, then this is 1 less multiplication going that direction. Okay, and then we have dot, dot, dot in the center here. I wish I wouldn't have smudged that right there. That's okay. We'll get there. So this should hopefully make sense, especially when you think about the numbers here. When you think about the numbers, you multiply by 2, by 2, by 2, and then eventually you have a last term multiplied n minus 1 times. And so that's exactly what we have here. Last term, n minus 1 times, n minus 2 times, and then we fill everything else in. All right, now what I want to do is I want to multiply this series by r, the common ratio r, and I'm going to write that down directly underneath it, and then I'm going to subtract it. Why are we doing this? You can't predict ahead of time. This has been proved a long time ago by people that played around with it and figured it out that it works. So we're going to do it, but don't worry so much if you say, well, I never would have figured that out. That's okay. I didn't wake up this morning and decide that I was going to do this either. All I care about is that you understand what I'm doing. So let's take this exact same series and multiply by r, the common ratio r. And I'm going to change colors to do that. The common ratio r is r times s sum n. So I multiply the left-hand side by r. I must also multiply the right-hand side by r. The first term is this, so I'm going to multiply by r. But I'm not going to write it underneath it. I'm going to multiply every term by r, but I'm going to shift the terms over. So I'm going to multiply by this, and I'm going to write it down here, t1 times r. Why am I not writing it down here? Because ultimately I'm going to be adding these terms together, and these terms go together. I could write it here, and then I would just have to collect terms, but it's going to be easier if I line the terms up. So I multiply by r, I write it here. I multiply by r here, and I write it underneath here, t1r squared. I multiply this by r, and I'm going to get r cubed, but that's going to fall into the dot, dot, dot area, so I'm not going to have to actually write that. It is there, it's just not written down. It's in the dot, dot, dot area. And then I'm going to multiply the term right before this one by r. See, this will be n minus 3 right here. Multiply by r, you add the exponents, it'll be t1r to the n minus 2. Because this one's n minus 3 plus 1 from the r, you're going to get n minus 2. Then when I multiply this one by r, I'm going to have r, multiply all this stuff by r, but I'm going to add the exponent, so it'll be a minus 1 here. So it'll be t1r n minus 1. And then when I multiply by r to the last term, r to the first power will add with this, so it'll become r to the nth power. Actually, I forgot a t. It'll be t1r to the nth power. So all I've done is multiply by this by r, write it down. Multiply this by r, write it down here. Multiply this by r, write it down by here. Multiply this by r, it's in the dot, dot, dots. Multiply the term before here by r, it's going to be n minus 2 when you add the exponents. Multiply this by r, you add 1 to this, it'll be n minus 1. Multiply this by r, add the exponents, it'll be r to the nth. So you know it's legal to multiply any equation by whatever you want as long as you do it to the left and the right-hand side. So I've done that. Now that I've done that, what do I want to do? I'm going to take this equation and I'm going to subtract it from the one right underneath. I'm going to do a subtraction. Remember, when we solve systems of equations, we can add them or subtract them. That's fine. Okay, so what am I going to get? Sn minus this is just going to be Sn minus Rsn. Just this term minus this term. No magic here. What's this going to be? T1 minus 0 is going to give me T1. What is this term minus this term? Well, it's exactly the same term, so it's 0. What is this term minus this term? It's also 0. And all the terms in the dot, dot, dot areas are also going to give me 0. So let's just kind of do this. This term minus this term is exactly the same thing. It's going to be 0. This term minus this term is exactly the same thing. It's going to be 0. Here's a 0 up here minus this one. It has to be a negative t1r to the nth because it's 0 minus this, as I'm subtracting everything. So really everything canceled in the whole thing except for all of this stuff. So I have Sn minus Rsn equals t1, all of this is 0, minus this, t1r to the nth. So now all I have to do is clean up. I have an Sn here, so I'll pull it out, factor it out. I get 1 minus r on the left, 1 minus r. On the right, I pull out a t1. I'm going to have 1 minus r to the nth. Verify, you multiply through here, you get this. You multiply through here, you get this. Now we're going to solve for the nth partial sum. It's going to be t1, 1 minus r to the power of n, divided by this whole thing, 1 minus r, which is exactly what we said the partial sum should be. The first term times 1 minus r to the power of n divided by 1 minus r. And of course, because this is in the bottom, r cannot be equal to 1. We've already discussed why that's not that big of a deal anyway, because if the common ratio were 1, the series would be really simple and we could easily add everything together. Now, do I expect you to be able to recover or do a proof like this? No, of course not. I don't care about that. I just want you to know that you understand where it comes from, okay? It's legal. Every step is legal. We wrote the series down. That's legal. We multiplied this series by r, which is a number. It's legal to do that as long as we multiply both sides of the equation by the same number. Legal. It's totally legal to subtract two equations of one another. You know that. So we subtract it. And then when you manipulate terms, you're able to get an expression for the sum. And this is the sum that's presented in the theorems. All right? So put it in your back pocket. Make sure you understand where it comes from. But mostly we want to focus on, from here going on, how to apply it. So let's go to this next board and just do a couple of quick extra problems to apply it. What if I have a geometric series with n terms, where n is 8, and the common ratio between these terms is 2, and the first term is equal to 1, and I ask you to find the sum. The first thing you do is you say, well, the nth partial sum is, you should write this equation down every single time, 1 minus r to the nth over 1 minus r. Now there's 8 terms, so what I want is I want the 8th partial sum. Is the first term, which is a 1, times this, 1 minus r, but that's 2, to the power of n, but that's 8. There's 8 terms here, over 1 minus r, but again, r is 2, so it's 1 minus 2. So the 8th partial sum is, the 1 is just going to multiply out, so what do you have here? You have 1 minus 2 to the 8th power. When you take 2 to the power of 8, you get 256. On the bottom, you get negative 1. So here you have negative 255 over negative 1. So the 8th partial sum is positive 255. That is the final answer. Now, I always recommend, when we do these problems, not to just plug things in and, go on our merry way. Let's write the series down just so we know where it comes from. Since we know the first term, we can write the first term right away. It's 1. And we know the common ratio is 2. And we know there's 8 terms total. So what we're going to do is multiply by 2, because that's the common ratio, we'll get a 2. Multiply by 2 again, we'll get a 4. Then times 2 is 8. Then times 2 is 16. Then times 2 is 32. Then times 2 is 64. Then times 2 is 128. We have 1, 2, 3, 4, 5, 6, 7, 8 terms, which is what we said we were going to add up. So this is 8 terms. So it's basically the same series as what we started out with, but we just have one extra term. And if you grab a calculator and add these numbers up, you will find out that you get 255. And so that's what we're going to do. So I only have one more of these guys to illustrate how to use the geometric series equation. Mostly I wanted to introduce it. I wanted you to understand where it comes from, with the proof, and then solve some problems. What if I ask you, solve and give me the sum of the following series? 2 minus 6 plus 18 minus 54 plus 162 minus 486 plus 1458 minus 4374 plus 13122 minus 39366. How many terms do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terms. Let me just check. 2 minus 6 plus 18 minus 54 plus 162 minus 486 plus 1458 plus, I missed one. Let's see, 486 plus 1458. Oh, no, I didn't. Minus 4374 plus 13122 minus 39366. That's correct. So what we want to do is we want to find the sum of this. First of all, is it a geometric series? That's what we want to figure out. Well, if you think about it, you grab a calculator. If you multiply by negative 3, 2 times negative 3, you'll get the negative 6. If you take this and also multiply it by negative 3, 6 times negative 3, you're going to get the 18. If you go here and multiply by negative 3, you'll get this. Multiply by negative 3, you'll get this. Multiply by negative 3, you'll get this. And you go all the way through the sequence. So every term is just the previous term multiplied by negative 3. So we then know that it's geometric with the common ratio of negative 3. We also know that there are n equals 10 terms, because when you count the terms, you get 10. And we also know that the first term is equal to 2. So by being given the sequence, we can pull all of this information out, and that's all that we need to solve this problem. Okay? The nth partial sum is equal to the first term times 1 minus r to the power of n divided by 1 minus r. So if we want to find how many terms do we have? 10. The 10th partial sum, it's going to be the first term, which is 2, times 1 minus the common ratio r. R we said was negative 3, so you put it in parentheses, negative 3. Make sure you put it in parentheses. To the power of n, which is 10. And on the bottom, it's 1 minus r, but again, wrap it in parentheses because r is negative. It's a negative 3. So now we just have to crank through this. What do we get? 2 times, here's 1 right here, minus, what is negative 3 to the 10th? Negative 3 to the 10th is going to be a positive number, 59049. It's a big number, 59,049, but it's positive because it's an even power. The minus sign comes from the outside here. This evaluates to a positive number. Here, you have 1, this becomes a plus 3, so you have a 4. All right, so the rest of it is just simply math. The 10th partial sum is 2 times, when you do 1 minus this, you'll get negative 59,048 over 4. So the 10th partial sum is negative 29,524. Negative 29,524, you might say, wait, how's it negative? Well, it's negative because the signs are alternating, and look at the last number. The last number was 39,366. That's a negative number. This is going to pull the whole thing negative because all the other numbers are so much smaller, and so you end up with negative 29,524. So in this lesson, we have used the geometric series to the equation for the geometric series to calculate the sum of any geometric series we want. And all we have to know to do that, we do not need to know the last term, but we do need to know the first term, whatever that common ratio is, and however many terms we have in the series. We went through the proof of it. I hope you understand it. I tried to make it as clear as I can. The proof is important, but mostly I want you to know how to use it. And that's why we did these problems here. So make sure you can solve every one of these yourself. I have one more lesson in geometric series calculations that we're going to do. So follow me on to the next lesson. We'll get more practice with the geometric series.